name is Sebastian Haas. I will talk together with my colleague Nils Asmussen. We want to talk together about hardware-software design challenges for secure computing platforms. And so we are from the Barkhausen Institut. Louder, okay. We are both from the Barkhausen Institut, and maybe you don't know that institute so much. Let me briefly introduce our institute. The Barkhausen Institute is located in Dresden in Germany, and we are a non-profit research institute founded in 2017. We are currently about 40 people, but we are constantly growing from year to year. We are divided into 5 research groups plus 1 open lab. Open lab is more for public relations. I come to that later. And we are mainly funded by the state of Saxony, the government by the state of Saxony, but we are also involved in national and European projects where we get our funding from. We work in close collaboration with the university in Dresden also. Our goal is to increase the trustworthiness for the tactile Internet of Things. That fits very well to the HiPEAC vision in general, and that's why we thought we could give our latest research and kind of introduction in our concepts here today. Why Dresden in Germany? Dresden is a very famous spot for global industry players, and there's this network called Silicon Saxony. It is a network of more than 100 members in Dresden. It is one of the biggest IT cluster in Germany, and it includes top industry players like GlobalFoundries, Bosch, and Infineon, but also research institutes like Fraunhofer, Max Planck, Leibniz, and also the Barkhausen Institute. And as I said, we are working in quite close collaboration with the university in Dresden. The university is already very excellent in all those areas like hardware, software development, connectivity, that means communications, signal processing, so very strong in 5G, 6G development. And we don't want to copy that research at the Barkhausen Institute. We want to be a kind of glue in between, where we work on the work in between, where we have some more overhead. Also, another point is that we do not primarily educate students, which is the work of the university, so we can focus on the works in between, who are mainly too much for the university. And as I said, we also have the open lab, where we want to go out to the public and present the research in a very simple fashion that everybody actually can understand it. So what we do in the open lab is, for example, we build demonstrators like such an air hockey table where everybody can play and where we can show the latency of IoT applications. We go also into the museums, present research in a very simple fashion. And the latest thing, we build up a computer game where you can feel the latency and the throughput which is needed for a communication system, for example. The question we want to tackle today, and what we actually tackle every day in our work at the Barkhausen Institute, is how can we build a trustworthy and dependable IoT device. This need not be an IoT device, could be any electronic device like a workstation up to an HPC infrastructure where you everything which is connected to the internet. So questions here are, for example, from which attacks do we have to protect our IoT or our device in that case? And how can we design secure hardware and software? What are the costs for that? Which components can be isolated or which must be shared and which can be isolated? And then also, how can we combine hardware, software, including the operating system, to build up a trustworthy device in general? At the Barkhausen Institute, we do that in 3 key principles or key concepts, you can call them. The first one is physical layer security, where we design efficient encryption methods. A very famous example is here, if you have, for example, a sender and receiver like Alice and Bob, and they can derive an encryption key out of the parameters of their communication channel, because this communication channel between them is very unique. And if there's now an attacker like Eve, she would see another communication channel or other parameters because of other reflections. They could not derive the same key and cannot get into this communication. It's the idea behind that. The second key concept is joint communication and sensing, very simple, where we just combine communication, so data transfer, including radar, for example, to measure the distance with one single wave, with one single signal or waveform. And the third key concept is actually what we want to talk about today, combining hardware, software, operating system to build up a secure and trustworthy IoT device. One thing from our side, as I said, we are constantly growing and we're always looking for new and talented people. Please have a look at our website. There are always some open positions. But now for today, this is the outline for today. In the first part, we want to present some hardware software vulnerabilities and attacks we face today, which are very typical. Second and third part is then we think of state-of-the-art concepts, how security is applied today on the hardware as well as on the software level. And number 4 is then where we present a little bit our own research on tiled hardware architectures and operating systems. So let's go into the details now. Number 1, hardware software vulnerabilities and attacks. I start a little bit at the beginning. I have here the hardware supply chain, so in a very simple form. So you all know that when you want to fabricate or manufacture a device or a chip, you have to go all these steps. Could be also some analog hardware, antennas, whatever you can imagine. And basically all these steps you do not do on your own, are untrusted. So it already starts that you build into your chip, you build some third-party IP, which are actually black boxes for you. You don't know the exact behavior. You just have to take them and their behavior as it is. There's also PDKs, libraries, software tools you use. You never be sure if they behave like you want. And this goes on in the manufacturing, the foundry. You have to trust the foundry that they build exactly the same chip you want to build there. Also packaging and testing here, everything. The difficulties are here that these things, for example, if you have physical implants from the foundry, they are very easy to hide, or if you have an implant on your PCB board, nobody would see that. Also, malicious behavior may resemble to device imperfections that you say, oh, this device is broken, but no, there's a hardware Trojan on that, or for example. Also, if you detect this compromised hardware, it is very expensive to replace. In the worst case, you have to redo all these steps of the supply chain again. Some more details here in the chip design. There are also a lot of works and papers going on where some of these topics are presented. As I said, malicious design tools. When you think of a design compiler, your synthesis tool, for example, you never know if this tool adds some additional logic in your circuit, which then in the next step after the chip has been fabricated, it is triggered for a simple access, and then it accesses something you don't know. You have to trust the designers, the humans, of course. And yeah, there could be hardware Trojans, as I said, or compromised IPs you have to use in your design. One example from here, which was some years ago, there was a hard drive which was not empty. There was, on the hard drive, there was a code running as soon as you plug in that drive, and it started to search for passwords and accounts on your computer. So never be sure that when you buy a hard drive that is blank and virus-free. On the other stages, we also have Some kind of attacks like firmware modifications could be already during the manufacturing or during the packaging process. Reverse engineering, that somebody takes your chips, probes them, and try to find your secure IP, for example. Also physical attacks, where we can probe things, where we can switch voltage and supply voltages or frequencies to bring the chip into a state or into an unexpected, undefined state where you don't know exactly how it behaves. And then you could read out data or leak some IP there. This is the hardware side, but there are also attacks on the hardware, on the software side. So maybe you already know there are the usual things like buffer overflows, denial of service attacks, memory dump. For example, there's this famous example of cold boot dump, where you reboot or reset your processor, and when it starts again, you boot your own system on that, but the data from the previous run is still in DRAM or in memory, and then you can read out that. If you inject some faults, we also can bring the processor into an undefined state. Ransomware, also very well known. Reverse engineering, also from software side, replay attacks. And then there are also so-called side channel attacks, which we mainly bring together with these security issues like spectral meltdown, foreshadow, microarchitectural data sampling. These are mainly because there are hardware bugs in these general purpose complex processors, and these complex features like out-of-order execution, speculative execution, or processor internal resources are used, and they're so complex that there's always one possibility to get a side channel and to leak private data there. And attackers then may bypass all the security features of the processor itself, and then they have access to the operating systems, the applications, and so on. The mitigations are complex as well. They're mainly similar complex like the features they introduce. They introduce the problems. So the question we also discuss a little bit today is, should we still trust these general purpose cores? Can we use them to properly enforce isolation between software components, or do we have to go back to much more simpler cores and bring in the security on another stage? And when you now see there are hardware attacks, there are software attacks, how can we do that we bring in security? And we argue that because of that, security is a cross-cutting concern. Security has to be concerned in every level of your hardware-software stack. And what are I want to introduce here the first problems you actually, or the first ideas you would have primarily when you think of security in all these levels. For example, on the hardware side, you would say, okay, we need some kind of root of trust, which is our real trust on the hardware side. Could be some cryptographic keys, physically unclonable functions, or this key concept I presented before. This is physical layer security, where the root of trust is basically the communication channel and its parameters itself. And hardware should also allow us to separate security critical components from each other. This is the basis from the hardware side. When we look into the operating system, here it is actually responsible for managing the communication between applications. And also here we need some security, because the operating system should also properly isolate applications from each other by using the root of trust from the hardware side. So we have the first connection here between them. And also application side, we want to use so-called trusted execution environments to isolate applications from each other. And they are also managed by the operating system and also based on the hardware features we put into the security. So that was that part. Now let's go in each level. We want to take a closer look now. let's start with the hardware part and what are the state-of-the-art concepts on that level. Traditional hardware architectures are built like this, what you really have in such notebooks like Intel and AMD processors. You have CPUs, GPUs, I/O interfaces or accelerators. They talk over a system bus, which is the foundation. They talk to or they access a shared DRAM memory. And to bring in isolation here, we have then MMUs, so the memory management units. And for I/O interfaces, the same are here than I/O MMUs. They are very tightly integrated into the cores. And as I said, they're used for memory protection and translation to the shared DRAM. And they are also mainly controlled by the operating system. The same applies for the I/O MMUs here. But the problem is actually these features here, because these are tightly integrated into the core. So if we want to trust the core, we also have to trust these memory management units. And also, if we think of scalability, how can we bring out the operating system from these MMUs, and how we can scale the system, because the system bus would not scale to hundreds or thousands of processors. And like we already heard today, there are so-called tiled hardware architectures, very famous. It's just an old idea, but it's very nice for security concerns. So in a tiled hardware architecture, tiles are already physically separated from each other. We have a network and chip as a foundation, as a central communication interface here to ensure the scalability. And still we need some kind of isolations mechanisms here. So I called them memory controllers, which sit at each NOC interface here. Could be the MMUs from this traditional hardware architecture if we have some very general purpose cores. Could be also some custom memory controllers like DMA controllers or very simple things. In comparison to the traditional hardware architecture, there's also a lot of communication going on between these components, not only to the DRAM, which is not really a shared component here. So the challenge is to provide a very suitable programming environment. This is then the software challenge. In the next slides, I want to present that this idea has already been taken into account. There are a lot of tiled architectures. A very famous one, the Tile multi-core processor, formerly from Tilera. It's now Mellanox for networking, multimedia, cloud applications. Here on that version, there are 72 processors, very homogeneous architecture. All cores are cache coherent, so there's actually no isolation between them. Then another example is the cell processor. Maybe you also know that quite old thing here, also a heterogeneous tiled hardware architecture. They already introduced some DMA controllers to protect each tile from the others and to support digital rights management. Another example here, the Tomahawk architecture, a heterogeneous multiprocessor system on chip, mainly for SDR applications. Also here we see memory controllers for application isolation. In summary, actually these architectures build up an tiled hardware architecture because they want to parallelize and scale their system. And in a second thought, they then focus on security, but security is not the primary focus of these works. Other tiled hardware architectures, yeah, we have heard that already in the morning or today. The invasive many-core architecture, also the Calray MPPA processor, another example for a tiled architecture. I think we will hear about that tomorrow. And also here to mention the M3 architecture was built actually from people from the Barkhausen Institut. We take this approach because also this M3 was initially built to build up a heterogeneous parallel system and not initially for security, and we take this approach and add security there. There are also other works going on which do not build a tiled hardware architecture. They just build these memory controllers which are attached to each network on chip interface to the processor. In this work they have a memory protection unit which filters the transaction. It's the research work here. Also a very similar one, data protection unit, also attached to each network interface to protect the memory translation, the memory accesses. This can be configured during runtime by this network security manager. Another example here, more from the industry, from the company Sci5, also very well known for their RISC-V processors. They built up an open security architecture for multi-core systems with application and memory isolation. So this is their first focus is to build up a system where applications are isolated. So they use these so-called world IDs, which are each process and each memory or cache line has its own world ID. And when a processor or a process want to access a cache or a memory, this world ID is checked, and they could decide if the access is allowed or not. As a second focus, they also built in some entropy-based and cryptographic accelerators into the system to build up the security features here. So in summary, as I said, when we think of the hardware level, we saw that tiled hardware architectures are very good from a security point of view because we can physically separate the components. We have then memory isolation achieved by these custom memory controllers, like, for example, MMUs or DMA controllers. But this was only the hardware level. The problem is still here, how can we provide a suitable programming environment? How can we involve software? And how can we involve the operating system? Because, as I said, security is a cross-cutting concern. So, and this is now the part to go to the software, and I hand over to my colleague, Nils, please.
Okay, so then let me continue with the software side. So at first I want to start with the traditional software concepts that you probably all know. So at first we have a process which has its own address space and thereby isolates different applications from each other. And on at least typical traditional operating systems like Linux, it means that all resources in the systems are visible to the processes, but whether you actually have access depends on with which user this process is running. And the different address spaces are based on a hardware feature on the memory management unit, similar to the other features that we will see here. The next one is the container, which is becoming more popular recently, which is basically also just a process, but now with restricted visibility to the system resources. So for example, it could have no network access at all and just access to a part of the file system. And since this is also based on address spaces, based on processes, this is based on the memory management unit in terms of the hardware. And last we have, for example, a virtual machine, which allows you to run multiple virtual computer systems on the physical computer systems, which is also often based on a hardware feature on hardware-assisted virtualization, like Intel VTX, for example, and that then provides a separate CPU mode that runs where the virtual machines are running in, and maybe other support like for page tables and so on. However, typical operating systems today, like Linux, for example, are pretty complex and therefore also difficult to trust. And this is why we see a development towards more and more trusted execution environments, as this is called. The probably most famous example is Intel SGX. All of them try to remove the operating system from the trusted computing base, so from the amount of stuff that you have to trust. Intel SGX is an extension for x86 that it allows so-called enclaves. So this is how they call these trusted execution environments, These are protected from the rest of the system, so in terms of confidentiality and also integrity. And this is based on memory encryption and also has remote attestation so that you can actually prove that the communication partner is properly secured by SGX. Similarly, there is ARM TrustZone, which goes also in this direction, which is an architectural extension for ARM. Here we have an additional CPU mode that creates two worlds, as they call it, a secure world and a non-secure or normal world. And here is also noteworthy that also the memory and devices are aware of the CPU mode in the requests that are sent to them. And therefore, they can also, for example, enforce that only the secure mode can access certain devices or certain parts of the memory. These were the industry solutions. Also in terms of research, there are a lot of approaches. One of them is Sanctum, which is a bit similar to SGX conceptually, but doesn't use memory encryption. And it's also mostly software-based on RISC-V in this case. Because SGX is this big blob that nobody really knows how it works. It's mostly implemented in microcode, and therefore here it's mostly implemented in software. They have a small hardware extension for page table isolation, and most of the rest is running in software in this most privileged CPU mode, the machine mode on RISC-V. And they also protect not only against software faults, but also software attacks, but also against side channel attacks by using page coloring and thereby making sure that they don't interfere in the caches with each other. Another example is the Hex5 multi-zone security, which is a bit similar. So it's also based on RISC-V and also has in this case, called nanokernel, so some component running in the machine mode. And with that, they isolate applications into different zones. So they basically use the physical memory protection feature of RISC-V to create different memory areas where the individual components have access to. Okay, so the common goal here is to remove the potentially complex operating system from the trusted computing base and thereby run a security critical application on such an untrusted operating system. They all, in one way or the other, do that by either extending the core or leveraging the core's features that are already available to create such enclaves or trusted execution environments. However, unfortunately, it's not that simple because the first problem is that the operating system has quite a large toolbox available to still spy on enclaves. And there are various works that show that you can actually see what the enclaves are doing. For example, by observing cache misses or letting the enclave produce cache misses, let it produce page faults, doing scheduling tricks, and so on. And for example, there is a work that shows if you know that the enclave is doing image processing, you can actually extract the whole image that is being worked on. So the S is actually quite powerful. And second of all, which is kind of connected to that, this approach is inherently vulnerable to side channel attacks because the enclaves are provided by the very same core that has potentially these side channel attacks or these side channel issues. And this raises the question whether we still also should do something with the operating system. So maybe we cannot just get rid of that from the trusted computing base. Maybe we have to actually improve on the operating system's trustworthiness. And to go there, let me first introduce the problem with the typical operating systems like Linux, for example, so the monolithic operating systems. So you can see a picture here where you have the cores at the bottom, then you have Linux running on top of the cores with lots of components. So I don't want to go over all of them, but you can see it's all the things that the operating system provides is implemented in this big blob, like file systems, memory management, network, lots of drivers. And then on top of that, we have the actual applications. And the problem with that now is that if you, for example, find a single exploitable bug in some driver, let's say, which is pretty common actually, then of course it compromises the driver itself. That's kind of unavoidable. But because there is no isolation in any sense between these different components here, it actually does not only compromise this driver, it compromises the whole kernel. And this means it's basically game over. So the attacker has access to everything and can do whatever it likes. There are, of course, already solutions for that. So one solution is the so-called microkernel-based approach, which has the idea that you should we move most of the components out of the kernel. So here you can see we have a similar picture with the microkernel running on top of the cores, which only contains the minimum amount of features that are necessary to run the rest on top of the microkernel as normal applications. And which is typically something like process management, so to have multiple processes on top, and inter-process communication to let them exchange information. And then on top, you can see we have all these components that we had before, now running in user mode, so in the unprivileged CPU mode, which is making them less powerful. And also they're isolated from each other, so all of them are running in separate address spaces. And therefore, if we have the same bug again, which of course can happen because this is not what the microkernel approach solves, so we have the same bug in this driver. In this case, it really just compromises the driver because the fault is contained within this driver. So in other words, you need more than that bug in order to actually cause harm to the system. So you need multiple bugs to really cause harm. Okay, so in summary, your microkernels reduce the attack surface and with that also make attacks much harder. And this is achieved by providing most of the operating system's functionality by isolated user components. Unfortunately, as we already mentioned, security is a cross-cutting concern, so only doing microkernels is actually not enough today because there are quite some challenges from the hardware side. So at first, we have the systems get more and more heterogeneous. Second of all, we want to integrate increasingly third-party IP blocks because things get more complex and therefore you have to have other vendors producing things and then you might not trust them. Then we have the side channel issues in general purpose cores. So there are other challenges that we have to deal with and not just software bugs, for example. Okay. Then let me go a bit more into detail on these challenges. So at first, the heterogeneity challenge. So we have already heard today about accelerators. So of course, we want to use them. So they give us a lot of performance. They give us very low energy requirements. But unfortunately, this is actually a challenge for operating systems if they want to really include them into the systems. Because the typical approach of just having one shared kernel running on all cores, as we have seen that before, does no longer work if you want to really include these accelerators into the system, meaning that they should become first-class citizens, kind of. So they should not be just devices, but you actually want to include them in the sense that you could have an application using the GPU, using the SSD, using the TPU, let's say, and combining them in arbitrary ways. And if you want that, then it actually gets more complicated for the operating system. So the operating system needs to be prepared for these potentially very different feature sets of the different processing elements that we have in a system. Second of all, we have untrusted hardware components. So we have at first components like a modem, for example, that you cannot build yourself, and therefore you have to include that from somebody else. But then you should maybe not trust it. Because as we have seen in the past with this Broadcom incident, for example, where a remote attacker was able to completely take over the system by exploiting a bug in the Wi-Fi chip, there we have seen that you have to properly isolate these things in order to be able to integrate them without having to trust them. Then we have seen, as Sebastian already told you, that we have these side channel attacks in the complex and modern cores that allow attackers to leak private data from other applications, other SGX enclaves from the kernel. And they, in some cases, bypass all the security measures of the core, like address spaces or virtualization and so on. And the thing is also that these side channels have been lurking in the CPUs for quite some time, and nobody found them. Probably also due to complexity, because these are complicated interactions between different components of the CPU, which make it really hard to find, especially systematically. And this kind of also raises the question that Sebastian already mentioned, like, should we still trust these cores to properly enforce isolation between components on top of them? Okay, so what can we do? Let me now come to the last part here, to the tiled architecture and microkernel-based operating system that we are working on. And I want to start again with microkernel-based systems because this seems to be, at least for the software bugs, a good starting point. So let me go a bit more into detail. So you can see a similar picture as before. So we have the microkernel, we have some applications and services on top of it, and we have communication channels between them so that they can exchange information. And then we have that the microkernel is basically responsible for two things. The first one is the management of the communication channels. So it has to know which one can communicate with which other ones. And second of all, it is responsible to enforce the isolation boundaries that we can see here. So enforce that the address spaces are properly enforced and properly isolated from each other. And this is done with the help of a hardware feature, or of multiple hardware features actually, typically user kernel mode and the memory management unit for address spaces. And now if we look at one of these challenges, for example, like the heterogeneity challenge, we can see that it doesn't directly translate. Because if we have other components like FPGAs, TPUs, GPUs, they don't have these features necessarily, or at least not in that form. So we cannot just run a kernel there. We cannot isolate different components on top of them. Therefore, we have to do something different if we want to use this microkernel approach. OK, now to our approach here, which is a hardware operating system co-design. So in a sense, we are asking the question, what if we could change hardware? But we want to keep it realistic, and therefore we want to not assume that we can change existing components. Like we want to take the cores, the accelerators, and also the network on chip to connect them in such a tiled architecture way. We want to take them as they are and not change them. However, what we want to do is we want to add a new hardware component, which adds these features in the sense that we find in some of these components, in some cores. And this component is the Trusted Communication Unit, the TCU, which is now sitting in each of these tiles, as you can see. And this is, at a really high level, implementing the features that we need in order to apply this concept to such a tiled architecture with very different types of processing elements in there. So it's a communication unit, as the name implies, and this is why we can use it to communicate between different tiles. So you can have message-based communication, for example, or memory accesses between these tiles. This is the hardware part, and then the operating system part looks like this. We have the kernel running on a dedicated tile, the kernel tile on the top left, as you can see. But on this tile, there are no applications running. The applications and services are running on the remaining tiles and are then remotely controlled by the kernel. The kernel is mostly responsible then for establishing these communication channels for the applications and services. Coming back to the split into management and enforcement that we have seen before, it's a bit similar, but also different here. So we have at first the management part again being done by the kernel. So it manages the now TCU-based communication channels. But the enforcement has been moved out into the Trusted Communication Unit. So the TCU is responsible for enforcing isolation between tiles, and the kernel is managing these communication channels. And with that, we address these three challenges. So at first, we address the heterogeneity challenge by introducing an abstraction, a uniform interface, because now all tiles have this trusted communication unit, which at first make it easier for the operating system, because the operating system mostly deals with establishing communication channels, which works the same everywhere. It also makes it easier for the applications, because the applications can more easily create collaborations between arbitrary types of processing elements, because also all of them are using the TCU, so that all of them can communicate in the same way. Second of all, we address this untrusted hardware component challenge because all hardware components that we integrate are protected by the TCU, which means we control to which other system resources it has access to. And last but not least, we also address the side channel problematic because we can use physical isolation between these components. So if two applications are running on separate tiles, they are physically isolated from each other because tiles don't share any resources. And furthermore, we also have the kernel physically separated from everything else because it's running on its own tile. And with that, we also can shield kernel from these side channel attacks. Okay, Then let me go a bit more into detail about the communication at first. So the TCU provides so-called endpoints to represent communication channels between TCUs. And there are a certain number of them per TCU, and these can be configured at runtime to different types of endpoints. The first type is the memory endpoint, which gives you access to a piece of memory, for example, in DRAM, which is a contiguous range, and you have byte granular access. The second type of communication channel that we have is a message passing channel, which is represented by a send endpoint and a receive endpoint. So the one that has the send endpoint can then send a message over to the receiver, where this is stored in some receive buffer. And also the receiver can send a reply back to the sender, which is helpful for all of these remote procedure call workloads that we have in microkernel-based systems a lot. So as we build a microkernel-based system again on top of that, we have a lot of client-server communication where you have requests being sent from the client to the server and then back a reply from the server to the client. Then a bit more about the isolation. So as I have mentioned before, so some of these components, some of these processing elements might have already protection features like a memory management unit or user kernel mode, but not all of them might have that. So maybe we have a TPU, for example, that doesn't know anything about that. And therefore, we have now an additional protection layer with the TCU that protects these tiles from each other. And the way that works is that only the kernel tile can establish communication channels. So the user tiles cannot add or change any communication channels. However, the user tiles can use the established channels, and they can use them without involving the kernel again. So the kernel is just setting up a channel, and then afterwards the applications can directly communicate with the TCUs. And also with that, the applications basically run as trusted execution environment or in trusted execution environments by default, because if you run them on separate tiles, then they are isolated from the rest of the system. A bit more to the operating system. So the operating system is called M3, which either stands for microkernel-based system for heterogeneous many cores, or alternatively L4 plus minus 1. So L4 is one of the most famous microkernels. However, it takes ideas from there, but it's implemented from scratch, mostly in Rust and a bit of C++. And it's a microkernel-based system, and that means that most of the operating system's functionality is actually not part of the kernel, but it's implemented on user tiles. So like drivers, file systems, network stacks, and so on, all are implemented or are running on user tiles. As I said, the kernel is managing the permissions. It's doing that with capabilities like other microkernel-based systems. And the TCU is the one that enforces these permissions. For example, it enforces that you can only communicate with the communication partners that are allowed for you, or that you have just read-only access to a certain memory area. Another interesting aspect here is that the kernel is mostly independent of the other tiles in the system. So for example, if you look at the file system, M3FS, whether this is implemented as normal software on a core or whether this is implemented on an FPGA, the kernel doesn't really care about that. So it mostly cares about the communication channels on the TCU interface, and it's configuring the TCU. And everything else is kind of not the problem of the kernel, but the problem of the ones that actually run there, like the file system in this case, which makes it easier to support heterogeneous systems. Yeah, then let me explain how system calls work, starting with the traditional way to do system calls. So we see the picture from Linux again here, where we now also see Linux is running in kernel mode and the applications are running in user mode. And if we look at the third application here, which is currently running, let's say, the core is running in user mode, as you can see on the top right here. And if the application wants to do a system call, it does a mode switch and switches into kernel mode. And then Linux is starting at a predefined entry point and can then handle a system call. Like, for example, involve the file system component to handle an open system call, let's say. OK. On M3, of course, we cannot do this approach because the kernel is running on a dedicated tile with no application on it, so we cannot do a mode switch. Therefore, what we do here is we have a a dedicated receive endpoint at the kernel's tile that points to some receive buffer in memory. And when an application is started, the kernel installs a send endpoint for the application, which is connected to this receive endpoint. And later, if the application wants to do a system call, it first prepares a corresponding message in memory, and is then instructing the TCU to use the send endpoint to send it over to the receiver, so the kernel in this case, which the TCU will then do. And the receiving TCU is receiving this message and is putting that at the corresponding place in the receive buffer. Then the kernel can look at that, can handle the system call in a similar way as in Linux, for example, and can then also use the reply feature to send a reply back to the application, like everything worked okay. Okay, so this is how system calls work, and this is actually how all message-based communications work. So this is also used between clients and server in the microkernel sense to talk, for example, from an application to a file system. So let's see how, for example, if file system is implemented just at a very high level. So here we have an application and we have the file system running somewhere. Both have their TCU, and we have the DRAM. In this case, we are talking about an in-memory file system, so the file data is stored somewhere in memory. And at first, we have a communication channel between the application and the file system, which allows the application to send requests to the file system. Like, for example, I want to open this file, or I want to read this part or want to get access to this part of a file. And most importantly, what the file system will do is it will configure for the application a memory endpoint that, that gives the application access to a certain region of the file. So after that, after going to the file system and getting this memory endpoint to access the data, it can just use the TCU to actually do the accesses. And since these memory endpoints can point to really large regions, this makes it really fast and scalable, because we just have to go once to the file system and then we can work a lot directly with the TCU to process the data. Okay, then let me explain what one of the benefits of this architecture is by looking at the trusted computing base. So I'm using an example here. So let's say we have a system with 4 cores and a 5G modem. You can see all of them have a TCU, and we have the kernel running on the left one here. And then let's say we have some control application that is connected to a physical device. So this is security and safety critical. And then we have another side, the so-called sender here, that is receiving events from the control application and is sending that out to the cloud. So there is a communication channel from the control application to the sender to send these events to the sender. And then the sender is connected to the network stack that allows it to send that out over the 5G modem. So that, again, there's a connection between the network stack and the 5G modem. And also, in case there is no network available, there is a file system where it can store that locally for some time and send it out later. And as I said, the 5G modem is connected to the cloud so that you can send them out and post-process them later. Okay, this is the basic scenario. Then let's look at the trusted computing base. At first, the general trusted computing base that all of them have to trust is that. So we have to trust all TCUs. We have to trust the kernel as well, because the kernel is the one that can establish communication channels as he likes, and therefore he can access every resource in the system. So this is the one that we have to trust. And of course, with that, we also have to trust the core the kernel is running on. But that's it. This is all of the general trusted computing base. So note that the other cores are not part of this trusted computing base. Also, the 5G modem is not part of it. And then we can look at individual trusted computing bases. So we can look at the TCP of the sender, for example. So the sender has to additionally trust the core it's running on, obviously. It also has to trust, to some lesser degree, the components it's using. So it uses the network stack, it uses the file system, and also indirectly the 5G modem. These cannot directly manipulate the sender or read data from the sender, but of course they can deny their service. Right? So if the network stack denies to send out these events, okay, then the sender cannot fulfill its job. Therefore, it also has to trust them to some degree. Most importantly, if we look at the trusted computing base of the control application, which is this safety critical component here, it only has to trust its own core, additionally to the general trusted computing base. Because everything else is not needed for its service. And therefore, the whole right part of the system here doesn't need to be trusted by the control application. So if we now imagine an attacker, for example, that attacks the 5G modem and tries to get into the system, it's much harder than it normally would be, because you have to find multiple issues and multiple components in order to actually get to cause harm to the system. Okay, now we have multiple prototype platforms that we use to develop this system. We have at first the Gem5 simulator, where we try out new ideas, because we can more rapidly do that there before building actual hardware. But we also have an FPGA where we actually build hardware for and run our system on that. And we also have prepared a demo, a quick demo for that. So at first, let me introduce the platform that we put on the FPGA for testing purposes. So you can see we have a bunch of RISC-V cores here connected over a network on chip. Each of them has a trusted communication unit. You can also see we have 2 DRAMs that we have access to, and we have a UDP IP stack in order to initialize all components, like load applications into memory and things like this. And we also have a real network interface card at the bottom here that we can use or do networking with. Okay, then let me briefly show that to you. So I will now start the system, which is loading all components into the memory. And then let me scroll up a bit. So you can see at first the kernel is starting. This is the red part here. And then the user components are starting. This is the root application that is the first one, and that starts the rest of the components. So you can see at first it gets some information about the system it's running on. So it gets some boot modules that it can start afterwards. It also gets a list of the available tiles, basically. So you can see we have a bunch of Rocket cores. We have also some Boom cores, so out of order RISC-V cores in our system. And we have also some memory in the DRAM that is available. And then the next part is the configuration file. So in order to start such a system, we have a configuration file that describes what components to start and what their permissions are, so what other resources they can access. So I don't want to go over that in detail now. But in the end, a shell is started, as we will see in a minute. And here you can see the permissions of the shell. Like it, for example, has access to the virtual terminal. It has access to the network stack. It has a file system, and we can also allocate some other cores. So this is basically what this configuration is saying. And then afterwards, we can see the components are started, like the virtual terminal is started, the file system is started, and so on. And then in the end, we have a shell. And then I can do the typical things here. So I can list the root directory, for example, or I can list the content of a file, for example. I can also use pipes, like piping the content of this file to WC to count the words and bytes and so on. Or we have an info application that allows us to get information about the running components, like the root component, as you can see, the virtual file system, the virtual terminal, and the file system, and so on. So with the shell, we are kind of in a bubble that has been created by the configuration file, and within this bubble, we can work and we can run applications and access the file system because we have got access to that, and so on. Okay, so far to the demo. Then, let me summarize the talk. So the point that we wanted to make is that security is a cross-cutting concern. And we are therefore using a hardware operating system codesign to address this challenge. So we have this trusted communication unit as a new per-tile hardware component that we add. And on top of that, we have a microkernel-based system called M3 that is running on this hardware platform and that takes advantage of the TCU. So for example, we have seen that it does that for the file system by directly giving applications access to the file data. And this codesign has some benefits. So at first, it enables the usage of not just untrusted software components, but also untrusted hardware components, as we have seen. In particular, we can remove entire cores from the trusted computing base, which allows us, for example, to have more simple cores like the Rocket core, the in-order core for security critical applications, and then next to them for performance reasons out of order cores like the Boom core without having to trust the Boom core, or at least the security critical application doesn't have to trust it. And we also can prevent the known side channel attacks by that by using physical isolation, so not just physically isolating applications from each other, but also isolating the kernel from all of the applications running on the system. Yeah, and last but not least, again, we are hiring. So if you think this is interesting, you can find the open positions on this website. And with that, thanks for your attention, and we are looking forward to your questions.